It's difficult to overstate the importance of optimization to machine learning. Not every kind of machine learning model is fit using optimization, but it's by far the most popular way to do it. Optimization is a huge field and you could spend years taking classes in it, so we're not going to get very far into it here. Nevertheless, it's useful to see some of the concepts and hear some of the terminology that you'll no doubt encounter in any later machine learning course. Fundamentally, when we're performing optimization, what we're doing is performing a search. We define some set that we care about, here I'm denoting that as calligraphic X, and then we define a function f that maps members of this set onto the real line. We call this map the objective function, and we're looking for the member of the set that minimizes it. The idea is that if we can provide some kind of measure of goodness, or in this case badness, then optimization procedures can perform the search for us automatically. What I'm writing here is called an unconstrained optimization problem, and this is in contrast to a constrained optimization problem. Constraints come into play when the space to be searched is not necessarily defined in a simple way. Instead, we specify the set implicitly through a set of equality or inequality constraints. These constraints are typically expressed as functions of x. Here I'm denoting them as h and g. I'm going to save constrained optimization problems for another video though. To get started on the unconstrained problem, let's take a look at a simple function that just takes a real input and produces a real output. Here's an example of such a function illustrated in orange. The thing we're looking for here is the global minimum. This is the minimum of the function over the entire set under consideration. We contrast that with a local minimum, which is the minimum of the function restricted to just a small neighborhood. One of the big challenges of optimization is